Cái就答咗我啦。咁其實有一樣咧，同我都幾 friend 下嘅，以前佢就答咗我，I we miss you，即係好掛住我係嘛？咁我順便覆佢咧 ，me too 定
Hi, good morning, everyone. Sorry, good afternoon, everyone. It seems that we have some issue with the number of students joining this session. I'm afraid if some of you are outside Australia, not aware that AEST has changed. Okay, because usually at this time we have something like 70 to 80 people in the session. Now we only have 20 something. I assume some of you are not aware that in Australia we're now in the daylight saving time. So, well, let me make an announcement quickly to remind if someone are left out. Sorry about that. I should have realized this issue earlier. So I just quickly make an announcement in case someone are left without knowing that now it's the session time. Okay, yeah, let's wait for another maybe 5 minutes. You can ask me questions as usual in this time.
Hi, Jun, can I ask some questions?
Yeah, of course.
Thanks. It's about assignment 3. Just want to know for the assignment 3, are we going to make or can we make a PowerPoint for better demonstrations?
Yeah, you can, and you can also well, just talk against. Oh, by the way, give me a sec. I'm taking some audio. Sorry about that.
Okay.
I took some audio device. So. Wow, okay. Can you hear me?
Yep.
Okay, good. So are you talking about assignment 3 of discussing your implementation of the algorithm? Because you are in this group of students, I assume you are doing 32513, right?
Yep. Yep.
Okay. Well, it is okay. You can just go through your notebook and talk against your code and comments as if I was doing in our class against my notebook. That is okay. But if you think that is easier for you to talk with some slides, it is also okay. And you can choose to be present in the video, or you can just talk. And what I mean is your voice is there, then it is okay.
Okay, right. Also, even I do it without a screen showing, can I just submit like a audio recording, or I can't? I have to show something while I'm talking or while I'm presenting to you. Should I always have a screen showing? That would be either a PowerPoint or either a Google Colab notebook, something like that.
So I didn't get that quite clearly, but my understanding is you were asking whether it is okay to just talk without showing notes or slides.
Yeah, exactly. Because I don't know, I haven't done any recording before. So with so if I can just show you like a PowerPoint, I can kind of do the recording, my voice recording or my audio recording first, and then I combine the recording into the PowerPoint. I don't know, like kind of video editing software. Or do you have any recommendations how we can do the recording? I don't know, for the screen recording for my desktop and also record my voice in. Do you have any like recommended software that I can use?
I demonstrated last time. I usually use OBS. This one.
Okay. Right. Is that easy to use? Do I have to do any editings afterwards?
No, this is really easy to use. You can just start recording the desktop. You click here. Well, it's recording the desktop. Like for example, I'm showing the implementation of my neural network, so on and so forth. After that, you just stop recording, and you can close it, and then it will be somewhere, depends on your system. If it is Windows, I don't know what is in Windows, but probably the same similar structure. In Mac, it is in your home directory and in the movies. So look, that is what has been recorded just a while ago.
All right. Okay. Right. After. Oh, and someone is also providing other options as well. Zoom. And okay. Thank you, guys. Yeah, I'll have a look. Yeah.
And I'm not sure if you have experience in that. And this comment is not only for this student, but also for all of you. If you are not familiar with presenting like a piece of technical work, that could feel a bit challenging for one to cover all the points from start to the end and not missing one, not over time. So it would be super helpful if you can practice with your peers. And also, I think one small skill to do that is you can just have a Zoom session like we do. And in the Zoom session, it is like you are talking to a real person. That makes things much, much more natural. And then you record the Zoom session. If necessary, do some, post editing, but usually that would result in a more
nature, more inviting presentation. So, but that is depends on you.
Right. Or I can just write a script beforehand. Okay. Yep. Thank you so much.
Okay.
Do we need to turn our camera on?
No,
During the
I
presentation.
have a yes. Sorry. As we discussed before, you can choose to be present in the video, or you can hide yourself behind the scene. Just your voice is there. It's okay.
Thank you.
So I have guitars here. Thank you, guitars. Okay, anyway, let us start. Now we have been 10 minutes.
Wow. So, can you hear me?
Yeah.
Okay, yeah, sure. Without using a microphone, I have to talk very loudly, a bit tiring. Anyway, well, for some of you, I don't know if you have received the announcement and and quickly joined the session. So if so, sorry for not sending the reminder earlier. So this is a small inconvenience of doing the remote session internationally. Anyway, let us start. Well, as usual, we have a quick review of what we have been, and then we talk about the roadmap of the next, not only this one, but the 2 sessions. And then we start studying our main topic, neural networks, today. So let's have a really quick review. Well, our story starts with machine learning. What is machine learning? We call that software 2.0. We need data. We need to believe there is some trend in the data to be discovered, and we do not have the trend. Otherwise, that would be software 1.0. And there are 4 elements in this task framework. So you need data. You need to have a range in which you consider the to be learned trend, and the to be learned trend is specifically in this subject we study the supervised learning problems where you have an input, have an output. Okay, data hypothesis, you have a selector that helps you to get one particular candidate in the hypothesis set that best describe the relationship that has been represented by the data, and you have a criteria to do the selection. And in section 3 and section 4, we have considered a particular sample model family where, given the data table, we treat each of the data attribute as some input node, and we give the one node one weight. We take the weighted sum of each data sample, and that will give us a number, and we decide anything that could be possibly interesting about the sample according to this single number. So in this way, we have simplified our possibility of describing the relationship. So here is what we call perception model. Then we have acquired a geometric point of view of this model. In the geometric point of view, we consider a simplified case where we only have 2 data attributes. We use one attribute as the horizontal axis, and the other attribute as the vertical axis of a space. And in this space, every data point corresponding to the coordinate described corresponding to a point where the coordinate is described by the corresponding data attributes. And we describe the, we consider linking from the origin of the space to the data point a vector, and the above discussed computational model is then to take the inner product of a vector, of two vectors, the W vector and the X vector. And then we acquire a geometric point of view of the model as doing color gradient of the space, and then cut the space or make decisions of the space according to the color, where the color is corresponding to the particular number given by the computational model. And in session 5 and session 6, we have considered another family of the models where the conclusion is achieved by if-else statements. That is very natural. However, the sophisticated, the skillful part of that is that we design a data structure that represents the logic relationship of the represented by the if-else statement using the composition of the node structures in this way. And then we have a tree-like structure, and we consider how to automatically compose such a tree from data samples. And this requires us to be able to compute at each point how pure the target distribution is. When we have achieved complete purity or 100% certainty or zero uncertainty, we see now we have reached a conclusion. We can return a decision. And otherwise, we can make further split, further investigation. By doing an investigation, we will acquire some bit of knowledge that helps us to split the data population into different parts, and each of the part, hopefully, we will increase the purity. Okay, and by doing to do so, we have studied a measurement of information that is called entropy. That is to consider all the situations, how long we would need to encode the situation in binary bits in an optimal scale. And in week 7, we have considered the uncertainty, not the uncertainty here, but well, somehow we inherit the notion of uncertainty. We consider the randomness or the stochasticity of learning. What is that? We consider the learning framework where we have a learner, where we have a set of hypotheses, where we have the loss criteria. Okay, after all that, the learning process will give us hypothesis, the learned hypothesis. Okay, well, even if we have fixed everything here, there is internal uncertainty here. Why? Because the input of the entire process is a set of data samples that has been randomly sampled from the black box data distribution. So because of this inherent intrinsic randomness, everything that we can achieve in the learning, using learning strategy, is uncertain. And one of the most relevant quantity that has this uncertainty is how well the model has performed. So usually that can only be measured using the model's performance in the learning in the training data set. So we call that in sample error. Okay. Because of the uncertainty we have discussed, this thing is a stochastic thing that depends not only on the learning strategy, learning algorithms, the criteria, it also depends on the data that has been given to us, which we do not have control. So we can only consider this quantity in a stochastic way, where we consider its difference from what really matters, that is the performance of the hypothesis outside the sample, which is the out of sample errors. And we think there is a bad thing if the difference between these two errors is too large. That means we have encountered a surprise. We thought our model behaves in one way, but actually it behaves another way. The observed behavior is deceiving because we have encountered a bad data set. The D happens to be uninformative with respect to evaluating this hypothesis. However, we have hope that the probability of this bad thing happens decrease with the number of samples. So this decreases quickly. Okay, so that is the hope of learning. And we then discussed another challenge, which is this guarantee is for one hypothesis, H. However, the H star is not just an arbitrary hypothesis. This H star has been selected according to the input data D. And so to keep this guarantee, we need to factor in the size of the candidates of the H star. So because this holds given a fixed H star, but now it is not fixed at all. It is according to D. So we would like this to hold for every one in the hypothesis, and that we have to factor in complexity measurement of the hypothesis. Okay, so that is where we where it comes from, or where the rule of thumb comes from, that when a model works for the training data, then simpler the best. The simple model tends to be more generalizable and to be less likely to overfit. So this is another aspect. In week 8, we introduced our first advanced family of machine learning model, that is Ensemble, which is really straightforward. We have a couple of weak models. We choose to use weak models because we want to limit this factor. To limit this factor, we want the size of H small. And because this is small, it is very highly likely that even we have searched we have exhaustively searched this space, we cannot find a good enough candidate. And this motivates to use multiple hypotheses from H to compose a complex one. where to compose the complex one, the challenge is we would need to let those individual weak predictors to be independent from each other. If you remember our example of bomb follows A, Alice, then in a 3-member committee, Alice will dominate the committee and therefore invalidate everything, every motivation of employing an ensemble. And we discussed slightly that doing that, the learning error bound of the ensemble family can be inferred by the learning error bound of the weak classifiers. So which is significant. It's one motivation of using this scheme rather than construct complex model directly. Okay, so that is what we have learned so far. And in the AdaBoost, sorry, I haven't finished the ensemble. In the AdaBoost algorithm, in the most simple algorithm, we just resample and resample our existing training samples in each of the iteration step. We train a weak classifier repeatedly and then combine them together. While in AdaBoost, we reweight our data first and then resample them and get a weak classifier and compute the classifier weight, while the good classifier have heavy weight and the weak classifier have less weight. And then we weight the samples where the ones that has been classified correctly get underrepresented in the next round of learning, and those ones that are challenging get overrepresented in the next round of learning. So that is one way to put together simple models into complex ones. Okay. And from today, in session 9 and session 10, we will consider neural networks. Okay, so which will complete this. I mean the taught lectures of this subject. We still have 2 guest lectures where we will have people from industry to introduce their experience of doing data science in production environment. Okay. So, but we are moving to close the gap between the theoretical discussion and the practical data projects by introducing the neural networks. Recently, I think most of you have heard of neural network because it is the hottest model family in the learning family, in the learning field. Okay, so I'd like to motivate the neural network models from our known old friend perception. Actually, neural networks is called multi-layer perception. You will find this term from time to time while if you study some work in neural networks. We will see the link shortly. Okay. So I would like to invite you to consider one challenge for our perception. Do you remember if I'm going to make a perception so that its prediction to be more or less positive in this area and negative in this area? we have discussed that this is unachievable using linear perceptions, right? And we can consider how to extend our perception model to achieve this. And our plan today is first, we discuss the motivation of constructing the neural network models. We will discuss in detail the computational model. And then depends on our time, we will consider how to derive, how to make a learning algorithm for this model. See, this is a super complex neural network hypothesis space, and we want an algorithm that allows us to search in the space. And which can perhaps motivate some of the future developments. And in the next session, probably we cannot finish every technical details in this section. We need to carry some material in the next one, and it depends on our time. We will try to cover some other topics in this field, but I guarantee you that we do not have enough time to cover even a global picture of this field. It's really, really rich and very, very fast forwarding. Okay, anyway, welcome to this very exciting field. And in future, you will be able to learn a deep learning subject, deep learning and convolutional neural networks, I think. So anyway, let's consider the foundation of neural networks. So, by the way, have I shown? Yeah. I thought I haven't shared my screen. Apparently I did. Okay. Where is the playground mode? It should be somewhere here. Interesting. Oh yeah, it's here. Okay, we start from our familiar model, perception one, as a perception model. So I know the code is here, but let's assume this way you can follow much easier. So let's do a perp. What is the essential part of the perp, considering that our input data have two attributes? And for now, let us forget about the constant offset. So the perception, because for the purpose of instruction, okay. So let's just bypass the initialization and def the predict part of our model. Given an input x, so the output should be some decision making. The decision making is according to some number a. If you recall our discussion here, right? And the A is the weighted sum of the input. Right? X is the input, and what is internal of this perception model is the weights, are the weights. So we need the weights, and the weights belong to self, right? So we need to give some self weights. Okay, that is what we need for a perception. And for perception, the decision making is very simple. Let's def. We just need to return the sign of A. So when it is positive, it is positive. It's positive one. It's negative one. So that is the perception model, right? We can visualize perception. So this is just to draw its behavior on a two-dimensional plan, because we have two attributes in the in each data sample. I haven't run this part, I think. P isn't defined. Sorry, it should be PP. What? Okay. Let us from now follow some convention in the world of neural networks. So for reasons that will become clear shortly, usually in the neural network model, we call the prediction forward. So it's just a prediction. Let's just make this very explicit by ramping predict using forward. Return whatever self.predict will do for X. Okay, so you can see this is just a ramping. Not very interesting. Okay, you can change this part, such as maybe 1 equals minus 0.5. Then you can change its behavior. What? No. Sec. Sure, won't change. When change this one, it will change a little bit. Okay. So you can see that means when the if you read the text on my screen, when the X is minus 1.45, okay. Okay, that means here, and the Y, this Y isn't the target value Y. This Y refers to this axis Y is 2. So it's here, and the output of the model is positive 1, so on and so forth. Okay. Well, because as we have discussed, this guy can only produce those straight line, which isn't quite as required for some applications. So we consider whether we can extend, we can generalize this model. We split several components in the computation separately. And study them separately to see if we can make some generalization for each of the components. Okay. One thing we first noticed is that, well, perhaps we can we can make some modification of the decision-making process. The motivation for that will become 100% clear slightly later. But now you can see that instead of making hard decisions, how about let us making soft decisions? How to do that? Let's do this. Decision making 2 maybe. So 1 over . Okay, now we use decision making 2 rather than decision making for the output processing step here. See what we have. More or less the same, but now things change smoother. You get it? So look, here is very close to 1. Here is very close to 0. But in between, you have a transition range, right? Okay. And now let us see if we can change the behavior of this guy. Well, and you can see that well, although now the transition is smoother, is gradually, however, you still have this straight line thing here, right? You don't change the ultimate fact that this model can only produce a straight line. Okay, we will consider this. So I'm to change the behavior of that straight line. Let's consider one thing. Is there anything that that prevents you to do something about the input data before applying that to the model parameter? It seems not. We perhaps be able to somehow. Sorry about that. I think I need to rerun here. To somehow do something here so that my coefficients, note that I have just changed the name of this variable. Previously, I called that width. Now I call that coefficients. The change of this, the name represents a change of my mind. It does not change this number at all, but that changed my mind. By calling that coefficient, that refers to maybe, I think here is a term that not necessarily an input data attribute, but some processed input data attributes. We call that features. Consider how about let's take the square of x0 and see how that will help us. Oh, look, we start being able to bending things, right? How about take the sine value of that? Look, although I still do not know how, but this change definitely put making boundaries like this within the possibility, right? I hope you get to this point. before we start to start to venture far from here. Okay, let me make a poll to see if we are good. So if you have questions, speak up.
I have one question, sir. I don't understand when making the square of our x0 created curved lines, or like making the sign of x1 makes it a circle. I don't understand that. Why is it happening?
But can I ask you a question? Do you understand? Can you try to understand what does it mean by those colors? Recall that this is basically not decision making. To be more specific, this is to produce a number according to which we make decision. Okay. Of course, I do not want to make such a lengthy name, so I call that decision making. Well, given this understanding, you would think you would in your mind be able to put it to consider an equivalence of producing a landscape using those colors. You consider this landscape, the color landscape, the color map. Similarly, as trying to produce those boundaries, because at the end of the day, you can see, let's make a decision. We cut things at 0.6, and then the 0.6 maybe height lines will be corresponding to some curly boundary here. Is that clear? So consider the 0.6 color here, and if you try to find every spot, every point on this plane where the color is same as here, you will find some curly boundary. Okay, that is the motivation why we are interested in producing some interesting landscape on the two-dimensional plane. And to produce this landscape, you might want to consider some polynomials or more complex functions, nonlinear functions of the input data. Otherwise, because if you just give them weighted combination, all you get would be some straight stuff like this. Okay, why you only get straight stuff? Because consider if you move from this point, the point where I'm pointing to this point, so the movement will taking you, you consider while in the movement, in any at any moment in this movement, and the tiny little infinitesimal change at this time while I'm moving, it would be just to add to a some delta x, some delta x0, some delta x1, and this increase would be delta x times w0 and delta x1 times w1. If the delta x0 and delta x1 will be the same, then the change in A will be the same. However, if you consider some nonlinear function here, then things change in an interesting way. Okay, when you, for example, moving from like here, moving from this like x equals 0.1 and move to the right, x equals 0.15. The change in A is not constant. The change in A does not depend on how much you have changed x. It also depends on where you were originally are. The change when you were at 2, x equals 2 is different from the change as where you were x at 0.1, even if the delta x is the same. So that is the essence of nonlinearity. Anything that is nonlinear, that means the change of the output does not depend on the change in the input, but also depends on where you were. And so that makes the interesting curves on the plan. And we will get into this part slightly more later. Okay.
Thank you, sir.
So if you still have problems, questions, let me know. I need to keep you a very clear mind before we forward on. Look, on the other hand, if you just want to use neural networks without understand how it works, then things will be much easier for you. There are thousands of tutorials on the internet that explains very interesting models and let you to get your hands dirty. I will encourage you to that after this study. And here we try to build a foundation of understanding the neural network models, which I think maybe in future to give you like more I think it's a more intellectual appreciation of the models that can helps you to find really interesting innovation from the ad hoc improvements. And on the other hand, to be able to, guess, to have a gut feeling of the feasibility of different models. Will that work at all? Okay, so that is our plan. If you cannot follow everything, try to, try to just get on and let the material settle in your mind later. Another question?
Oh, hi, Jing. Yeah, I'm just confused that give any values to how did they generate the plot like this?
This? Okay, this is easy. So I've just exhaust all the possible locations here, like this x equals like this x equals.
There's another function up there.
Which function?
I mean the visualize function. So
Yeah,
it's been set up
I'm
before. Okay.
explaining the visualize function. This is a trivial thing. Basically, I have just let my my model have produced have processed, I think, 2,500 samples, and those samples covering the entire range of this this plan. Okay, let's maybe look. I cover the range from -5 to +5. Okay, you can maybe try to cover more and see how that works. And let's call that x0 and call that x1. Okay, so let's call that A and see how this works. Now we will cover from -15 to +15, which is a much larger area. So let's have a look. What? Okay, let's try not to change. Okay, x0, x1, and a. So I need to keep the name consistent. So, but that won't be a good idea because I have used, okay, it's okay. Let's try. If we have other glitches, I will change that back. It takes slightly more time because it needs to process more data. Okay, so look, minus 15, positive 15, minus 15, positive 15. And this is x0, this is x1, and now it calls the output as A. It's just an visualization, okay? So let me change that back to save some processing time. You can do that by yourself. By the way, it is a nice way to get an intuitive understanding of how the model works. Sometimes you can do that very, very costly. See, in this way, you will understand how that works. And the picture is just an eye candy. Actually, it just worked on every single point like this. I will just make the step larger so that now we do not have a densely arranged array of points, but you can see the dot, dot, dot here. Okay. Change that back.
Yep, thank you.
Okay, now I think I have successfully persuaded you that now this possibility is within the range. We can, although it's a very simple perception model, we can somehow achieve very complex behavior of the model. But the very natural next question is, we just try this randomly? Or June, maybe I pay you $10,000 for 5 days of work. You as an expert try to design such a thing for me. Well, people back in like 70, I mean last century, 70, 80s, they did this. But then over time, people start to imagine, is there a more systematic, more principled way to approach that? So a very clever idea would be like that. Okay, look, now I want to transform here. I'll put my transform here. Let's copy this. Okay. Okay, call my perception X. So my perception X now accept some transformation of my X. Okay. Let's call it TX, transformed X. Wow. So I was withholding my introduction to what will be the clever idea. I'm showing. I'm not only try to tell you what is this idea. I try to tell you how that idea was come from. So this is what? Okay, this is just to repeat what we have now, and we can def our transform function x. Okay, we can just return on what we have done. X. The first attribute, we take the square, and the second attributes, we just keep it, or maybe we can do something like slightly more interesting. Take the inverse. I don't know. Maybe I will just blow up everything. Ha! Overflow. Ah, yeah. And you can see because I'm taking the inverse of that, when it cross zero, something bad happens. Whatever. Now we can make very bizarre pictures using this. Well, but look in this way. We now have one piece of extension at our hand. That is, okay, we can somehow invent something to transform the function, and we take out the transform function out. We take out the transform function and study the transform separately. The clever idea would be how, wait a moment. How about we just use perception itself to perform the transform? Wow, that would be an interesting idea. How to do that? Okay. Let me first put the transform function. Okay, this is one advantage of Python. Someone, if you have learned programming in Java or whatever, that would feel a little bit sinister, very evil-looking code. What you have just binding a function into a function. Yes, it's okay. Everything is an object in Python, even of a function. A function is none other than an object which has the capability of letting you put a pair of brackets and call it. So that is a callable function, a callable object. No more than that. So you can call that self.transform function. So if transform function is not null. So if you give me something, I will let myself transform exact. Otherwise, self.transform function would be just lambda, which means give me x, I give you back x. So which just means I do nothing. Okay, now I have a transform function with me. I then can call my transform function here, right? Well, if I'm just do this, you will expect this will revert back to the flat thing because I did not provide any transform function here. You can see this. Okay, because it revert back. It is a false back into this branch. I don't provide anything. It just use the default one. And if I provide this thing, it will become the behavior like previously. Okay, so now we can really change its behavior. Okay, let's do something interesting. X0, we can do one thing like that. What we will do, we will perp x do nothing. However, if you remember the do nothing thing, so like that. Okay, it's okay. If you let's review the do nothing function. If you do nothing, it will produce you something, but this is no longer a linear function of x, right? This is something that is nonlinear about x. That the change is gradually, but it's not a linear change. Look, here is very flat. Here you have a transition. Here you become flat again. So although the boundary itself a straight line, but the values is no longer uninteresting stuff. So I'm using one like that. I produce one like that, and the ppx maybe so 1 per x. Okay. 1 w maybe minus 2.0 0.5, for example. Okay, now I have two perceptions, and I will take another transform. Anyway, what I'm going to do is return ppx 0 dot forward x and ppx1 dot forward x. So look, basically, I have to another two perception. Okay, this is not appropriate writing. So these two perceptions will output their forward result to our previous perception here. Okay, and let's see the behavior. It's not that that obvious, but you can see that it's not linear anymore. You can see those slight bumpy curly thing here. I'm not sure if I can change something more clear here. Maybe not. Oh, sorry. No. That's my fault. My fault. I should put this here. Yeah. This will be obvious. Yeah. So the behavior of the second layer perception becomes much richer than as if you just put the data, original data, into its input node, right? This is the construction of neural network. I let you I give you some break and sorry, I give you some break. And we can discuss more if you have questions. Please do the pooling, so I know that we are on the same page and it's good to go. On the other hand, so this other demonstration code just to do very similar stuff here, but I'd like to construct from scratch, so you know how things come about when you need to write them from scratch. It's good for understanding. Okay. There's nothing to stop you or us to include a bias term here. So usually we do this, okay? This does not change the construction at all. You can see it can move the pattern around. It's just another model parameter, okay? However, what is essential thing is there has to be some transformation here. So you cannot just return A without this stuff. So usually you have another, you can have another option here, like the activation function. I can do this as well. So basically we follow the similar procedure. If activation function is not known, I will let my activation, it is called activation function for some reason. When you read literature, you will know, but somehow it is from the biological study of the neural system that our neuron will activate in some nonlinear pattern, stuff like that. But anyway, that refers to the decision-making procedure here. So if it's not known, we will let it to be just what has been given to us here. Okay, otherwise, we will let this activation function just to be say here, input output the same. Okay, so we can have a look at that, but this haven't been used. Sorry about that. Let's use this. Sure. Well, we can add the activation function to be decision-making too. Okay, we can add this activation function to be decision-making too. And here we can also let the activation function to be decision-making too. Okay, so this will not change the behavior at all because we just put whatever there has been into options. However, what will change its behavior will be, so how about if we remove this? Okay, let me remove that and let you see what is the change. You would find there will be some change, but the change is not essential. Okay, so the color distribution definitely changed, but from the global structure point of view, we still have what we have. On the other hand, okay, let's keep this activation here and remove the input activation. See what we will have. Well, it gets back. And no matter how you have changed the behavior, how you change even the number, look, you are not restricted to the same number of inputs as the input data. I will come to this point later. However, you change this, you still have this simple looping behavior. Why? Recall, I'm now going to the computational model of neural networks, okay? Recall the computation like that. I'm writing out one sample, so I just write x maybe 0, x1, okay? And you have the weights w1, w0, w1, right? I'm referring to this original perception. If you remember this, if you remember the computational model of the original perception as the inner product, and inner product is none other than the weighted sum. So, and the weighted sum can be written in the matrix multiplication. You can, when you write one row of numbers and one column of numbers, okay, and then you just go this way. From this part it goes this way. From this part it goes this way, and you combine x0 with w0, x1 with w1, go so on and so forth. This will produce one number a here. The beautiful part of that is this model applies to the prior layers as well. It also works with this guy. So you just consider the W's are the weights here, okay? And let us change a color, because now you have such an A, which will be input here. Oh, sorry. I miss. I think I have misinterpreted. This way, okay. And how about that guy? This guy will be linked from the same X, okay? Linked from the, let me move it here. This guy will be, I'm showing it clearly. This guy will be linked from the same pair of X, which means considering this guy's input is also the X. It's also from the same X, right? So this X goes to this one, and the same X goes to this one as well. So let's write down is this. So this is a really unconventional write-up of not using subscript or superscript, but using colors to distinguish the elements in in an array, okay? But you understand my point. And then you perform the same kind of computation and you get those red A, right? So put things together. You have an X, well, which is a row vector, and the W, maybe I put it here, 1, which is a column vector. So that is a W1, 0, W1, 1, you go this way anyway. And you have another W vector, which is also a column vector. Okay. If your X has some maybe P attributes, your W will correspondingly have P weights. And say if you have Q, neurons, we now call that neurons in a layer. Okay, now we have 2 neurons in a layer, but that is a flexible thing. Nothing stops you from employ more neurons. Let's have 3 neurons in a layer. Okay, maybe so the transformation can be to forward X. And now the final layer accepts 3 inputs. So it will become TX2 times self.W2. Okay, and now it needs 3. Weights here. Uh-oh, what happened? The couple of brains. Uh-oh, it's my fault. I think, yeah, I know what happened. Because of these ones have only 2 inputs and this one has 3 inputs. So I need to write it not in this hard code. I need to write it in a more reasonable way, which actually is easy. Zip. I'm zipping the TX and W. Okay, A is increased by W underscore times X underscore. And then I let it. Okay. Look, the behavior is even more interesting. So I'll just maybe add yet another one W3. Okay, this is. So what does that mean? Is the computation of one layer will become, consider that it's a data matrix, okay, with one data sample time a W matrix that is of P input and Q output. That is just a matrix multiplication stuff. Okay. So that is our forward computation of neural network. And what is more, consider the output of this, let that to be H. H would mean that A1, A2, and A3 that comes in for this sample, and that H, if you consider the weight of the second layer, we can just time that, for example, let it to be U. U would corresponding to this. I just call that U because I do not want to use so many W. So that has 3 weights here, the same number of the output of the first layer. So you have 3, and now it has only 1 output. So what happens is we can just use matrix multiplication layer by layer so that the computation is called forward. Okay. Well, what is important of this activation here is that if consider there is no such activation, then we would have the final output prediction. Okay, the prediction would be X times W times U. And the multiplication is associative. So if you call that something V, that will become F times V. And the whole thing is no more complex than a single perception. However, if what you are doing is to make activation after you have performed the first layer processing, then everything changed. It is no longer allowed to associate the further processing into this way. So that avoids collapsing the entire model. So I think so much I have interpreted all the forward computation of neural networks. Okay. And according to our plan, in the next step, I would like to introduce you the next very important step. Now we have, well, kind of the decision tree type kind of composing things, not using programming, but using data structure. And then the next step would be we want to find some way to figure out the numbers in the data structure so that the entire computation architecture behaves as what is required by the data. Okay, to do this, we would like to investigate the effect of each single model parameter on the output of the model. But perhaps we do not have enough time to go through this part completely in this week. Okay. However, I have made quiz 9 and quiz 10 both accessible to us. And anyway, let us go to today's quiz first, and then use the rest of the time to see how much we can go forward. By the way, don't worry about quiz 10. For quiz 10, we have 2 weeks time. Sorry, for quiz 10, I have set up the deadline in the next week, not this week. So anyway, I will try to go through the quizzes, and if you do not understand so much about quiz 10, don't worry. We still have 1 more week to study it. Okay. While I'm preparing the quiz, let me know how things go with you so far. I hope I have motivated you interest enough into studying this very fascinating family of models. Okay. So the quiz questions for this week, I mean quiz 9, are as follows. The first quiz is about the model structure related with some relationship. With some discussion about the computational model, where we have 4 input data attributes. One, 2, 3, 4. And our hidden layer, which means the middle layer, has 16 neurons. 1, 2, 3, 16. And then we have only 1 neuron in the output layer. So it asks if for each of the neuron, we both have the weights and the constant offset bias, how many parameters together in this model? Okay, recall our discussion here, right? So for this neuron, it would need 1, 2, 3, 4 weights plus 1 bias. For this neuron, it would need 1, 2, 3, 4 plus 1 bias. Okay. All together, those parameters have 80 elements, right? That is 16 by 4 plus 16. And for this guy, similarly as here, it needs the same number of weights as the previous layer's neurons. So 1, 2, last 3 plus 1 of the bars. So that 17. So altogether, we have 97. Okay. In question 2, in a classification problem, when there is no conflict in the training data, well, this is just a very conservative thing. That just means any reasonable training data. A neural network with 1 hidden layer, with 1 layer of neurons here, it will be able to achieve 0 training errors. I just telling you, the conclusion is true. Not only it can achieve 0 training error, the conclusion is that when you have a function from some x space to a number y, y is belongs to the real number. And if you have a neural network, and the neural network can have as many intermediate neurons as you want. In this case, this neural network can approximate this function as close as you want. So if you increase this m to whatever you want, you will have the precision, fixed precision, fixed desired precision. You can always increase this number so that the error between your approximation and the true and the desired f falls within this precision tolerance. Here is a kind of interesting story in the development of neural networks. When perception has been proposed, I think one very dominant figure, I do not remember his name, Chomsky, maybe, have proposed anyway the counterexample of the maybe 1, 1, 0, 0. This example. This is a simple example because this is none other than the exclusive OR in every maybe simple logical electronic circuit can implement exclusive OR function, and that had been used as a counterexample against the perception learning. Say, okay, this sample is this model is so weak, weak enough that even one logic gate cannot be achieved by all the learning stuff. If you remember the funny picture, let me find it. I hope I got that. Remember this guy say, hey, you have used such a thing without being able to achieve this, then what is the use of your complex machine? Well, that have this book, I think this book chapter or a book chapter anyway, has single-handedly dragged the development of learning-based artificial intelligence for more than a decade. And that is called the first winter of AI. Well, then after a while, people come back with a revenge. I think in maybe, I do not remember the time, 90. Oh, anyway, it's in 90s. A paper has proved that this is just because you haven't adopted the model into its full glory. If you have employed enough intermediate neurons, actually you can achieve whatever kind of complexity you would like. And however, people find if you really venture briefly enough into employing 1 million neurons, things get so complicated that you will force into this trap. Remember that? If you have a very complex model, the model can do anything, then everything it has been achieved is unreliable. So then in 1990s, with the development of the error bound theory, people find, well, maybe you are over complex and so unreliable. And so that comes the second winter of artificial intelligence. Okay. And until well, the story goes to 2006, Hinton has published a paper about, okay, perhaps we don't want a very fat neural network model. We want a tall one. So that comes a deep learning story, which continues today. Okay, and one of the key contribution in this factor is our video game card. Know what? Because the computation of the model depends on what? Depends on multiply numbers and add them together. Not much beyond that. Okay, and while you are computing computer graphics, I don't know if you have an opportunity to view any graphical model, although many of you have maybe play video games better than me. I'm not sure if you have the chance to see when things get buggy, maybe your game model stuck somewhere, then you will find those triangle meshes of the 3D model of the game. So basically you represent three-dimensional object in a computer graphics environment using those meshes. And when you try to draw those meshes on the computer screen, you need to go through every single pixel and figure out where the pixel falls in the graphic model and compute the lighting of the pixel and compute the lighting of the pixel and the depth of the pixel, so on and so forth. This is none other than a series of number multiplication and sum up. Same operation here. Then after the deep learning has been proposed, people find, okay, it's extremely large quantity of computation is needed. Well, one advantage I could take is that, look, when I'm multiplying this number, where is it? Okay. It's here. When I'm multiplying this number, maybe I'm computing this guy here. So I will consider the corresponding column. Okay, and I will multiply numbers here and multiply numbers here. However, when I'm doing things here, I'm considering multiplying these two series of numbers. Well, the only conflict is that I will want to simultaneously write into these two units. However, those do not conflict to each other. There is no risk of doing things together. Therefore, people find the computational tool to compute the video computer game is very helpful to do matrix multiplication. So people invent very powerful computational tools to leverage the streamlines in a video game card to do artificial intelligence learning with neural networks. That is a story. Okay. I hope maybe in the next session, we still have some time left, and I will introduce you how to use the modern hardware to leverage the computation into the graphic card. And now Google have invented maybe more dedicated hardware to compute that. because this computational paradigm has started evolving again. Okay, but that is another story. Okay. And question 3 just refers to what we have mentioned here. This. Without nonlinear activation, the hidden layer in neural network does not improve the model capacity because the network is equivalent to another one without a hidden layer. That is correct. To summarize, 97, true. Without nonlinear activation, the hidden layer does not improve the capacity. Yeah, this is the computational tool I mentioned here. Oh, where is that? I mentioned here. Okay. Using the remaining time, I quickly explain quiz 10 so that you know about it. Well, I know without a solid knowledge base, you just know about it. And we try to, maybe that will be a good outline of the next study. Okay. Where is my quiz 10? Okay. So, well, this is a really complex description. What I'm going to say is here. All in all, after given the X, given the network, given the prediction, then we need to compute a loss given the corresponding Y. This is only one number, one loss number. And what is important is we want to figure out the effect of each single model parameter on the one single error. So it would be, there are so many model parameters, 83, and one loss. So those two are wrong. And there are 83 corresponding partial derivatives. Partial derivative just mean, well, if I change partially the input here, how the output changes. So 83 model parameters, one loss, and 83 partial derivative to figure out. Okay, here, well, you do not have, we haven't discussed here, but the intuition is very, very simple, straightforward. What it's saying is like that. The activation function goes in this way. If the inner product you have computed is in this way, it's on this, and I'm making a nonlinear activation according to this input. So this would be the output. You might think nonlinear means things like this, right? Or you might think nonlinear means things like this. Okay. However, nonlinear could be things like this. This is nonlinear, although it's piecewise linear, but if you employ that, the complexity will be created. I show you a little bit about that. Return 0 if a is small or equal to 0, otherwise a is false. Okay, when the input is less than 0, it outputs 0. When the input is greater than 0, it will just output whatever input. Where is my? Let me change that to 3, and you can see how it will work. And to illustrate the effect, I will remove any more post-processing of layer 2. Okay, the layer 2 does not have an activation here. Look. There is still complex behavior here. Okay, and then we study. The study here is really simple, does not touch the nature of here. Is that, well, if I change the, at this point a little bit, how much the output will change? Well, 0. If I change a little bit here, so if I change the pre-activation, the result here, if change a little bit, then the output will change by 0. That is because, look, in this equation, when H0 is 1, U0 is 0.5, that will be 0.5, and here will be -1. So put together, we will be in the range of -0.5, and at this range, whatever change of the sum, the output won't change. So, and when the factors that contribute to the sum changes, the output will not change either. So the answer is 0 and 0. Question 3. So in the next time, we will discuss how to compute the effect of model parameters, especially model parameters of multi-layers. See, not only those parameters, but also those parameters affect the output, the loss of a neural network model. So let me, where is my window? Yeah. Here is the discussion goes this way. This is wrong. Given the gradient is difficult to determine how to change the model parameters. No, the gradient means we have figured out how the model parameters will affect the loss. So given the gradient, we know how to, which direction we can change. However, there is no direct way to decide how much we change, because the behavior is nonlinear. It is not like if I'm sure I'm changing this way, if I change this way, the more I will change, the output will change correspondingly in the same way. No, not like that. Maybe this part is a better illustration. So, for example, if you decide now to go this way, for example, if you want to go from the yellow part to the purple part, and now you want to go this way, it's okay. But if you go too much, you go back to the yellow part again. So the size of the change is the step size of the change isn't trivially determined. On the other hand, the other aspect it discusses is how difficult to determine the gradient, and that you can imagine. Look, this part, these parameters is closer to the final output, and these will have a more indirect effect, because if you change this will change the output of this, and this will correspondingly zero this change the final output. Therefore, due to some nature of the multiplication, the derivatives of the parameter set in the early layers close to the inputs tend to be inaccurate and damaged by numerical errors. Okay. So to summarize, 83 parameters, 1 loss, 83 partial derivatives, 0 and 0. Well, given gradient, easy to determine direction of change, but not easy to determine the size of change. Due to some difficulties, the gradient of the parameters of the early layers is more difficult to compute. Okay. Okay, I think we wrap up here today. Today we start from some limitation of the perception model, and then we discuss some intuitive motivation of extending the model, and then we discuss a clever way of extending model, clever and systematic way of extending model using none other than the model itself. We recursively build perceptions into multi-layer structure. So we haven't done more than 1-2 layers, but that does not stop you from extending things in this way. Okay, and we consider the computational model and formulate the model using matrix multiplication. Okay, and we slightly peeked into the future study of what we want to figure out the effect of changing the model parameters to the loss, so that we will be able to leverage the powerful computational model of neural networks to fit to our data. Okay, so before you go, let me see how the acceptance of this lecture. So let me know if you have get it. And if you have more questions, if you are more interested in that, you can stay for another maybe 1.5 an hour. Okay, if you have more questions, you can stay to ask me. Otherwise, I thank you for joining us, and have a nice weekend. Oh, have a nice week. This is not Friday, sorry.
So I have a question.
Yeah.
In perceptron, when we do the gradient things, I understand that those lines are perpendicular to our W vector, right?
Yes.
Yes, yes, but I'm confused when those lines became carved or in today's lecture. How I don't understand why those attributes produce those kinds of curved lines and circles sometimes.
Think
It's
that this
really
way.
confusing.
I understand your
Or
side.
when you were explaining in the class, I got disconnected because of connection problem. So
So if let me write in drawing in such a manner. Well, consider that x0, x1. When you have maybe a w in this way, you then have the gradient in such a way, right?
yep,
That is what you understand.
yep.
Wait. If you keep this w this way, don't mess up with your w. On the other hand, you do things in this way. Let's think about that. If you have changed that to be x to the square, x0 to the square, which you have done now is well, this was the original data space. To transform this data space into this one, you would need to ramp say let us see if this is 0, 1, 2, 2. So say 0, 1, 2. You need to ramp this axis in such a way that this goes to here, this goes to here, this goes to here, and this goes to here as well. This goes to here as well. So in such a way, although the gradient in the transformed space keeps the same, of course you do not have the negative part here. But if you unramp the gradient back to the original data space, you will have a complex pattern like that. You can consider it in this way.
Yep, but when those negative numbers go to the right side instead of the left side, I mean, when we run up things.
No. This is just an intuitive understanding. It's not a rigorous math. You cannot unramp those negative numbers. There is in the transformed space is not necessarily a space that that shares the same properties of the original space. For example, it may not be a Euclidean space, which means the elements in that space, when they combine with each other, may violate something. For example, in this data space, you will have confidence that if you go from here and here, you travel within the space without going out into nowhere. But after you have transformed, you may not have that property at all. So it's this is like an analogy. It's a way of understand things. It's not how things actually happen. To consider how things actually happen, you have to employ mathematical analysis.
Oh, I see. So how does our bias affect those lines that are perpendicular to W, further W? From my understanding, if I want to go up one lines or two lines, I have to increase the bias. If I want it to go down, I mean the
Yeah.
I mean I have to change the bias to negative numbers. Am I right?
Not necessarily. So let's change the W a little bit and see how things will change. How about that? Maybe to this. Actually, it has changed, but changed so little that you cannot clearly see it. How about if we do? No, we cannot do this. Okay. I don't think I can quickly give you a very intuitive illustration of that. But what happens in real world is we will figure out things like that. Look, considering if you have a data point here, okay, and you want what is the value here? So let's say 0.23. Okay. So, however, if you have a label here, so that the prediction is 0.93, and you have a label maybe 1.0 associated here, and what you will do is you will try to figure out, okay, now I have an error of 0.07. You try to figure out how can I change my W's. This is first neuron, first W, first neuron, second W. Maybe here is the first neuron, first W, second neuron, first W, second neuron, second W. And you go to another neuron, so that could be U0, U1, U2. Then you would like to figure out if I change this a little bit, maybe delta, how that delta will transform to the change in this error. And you do that, we will do that very meticulously, one parameter by another. And at last, we will have the DW1, DW12, DW21, DW22. We have a copy of this the parameter data, and this copy corresponding to our knowledge of if I change this parameter a little bit, how much I will affect the output of the model. We will discuss this skill in the next lecture.
Oh, I see. But I mean, those gradient divisions are like they are how can I say, they are just division, right? Not the data points.
Yeah, they are gradients. They are not data points. They are, now we have to decouple our understanding of weights as data points anymore, because now the weights are in a different space than data points.
Changing the inputs, I mean the attributes, changes the distribution of the observed samples, right?
Sorry?
I mean, changing the attributes. Let's say we make the square of x0. So does it change the distribution of the observed samples since we change the we change the values.
No, you don't change the distribution of the samples. You just you just want to, what you have said is just to evaluate the model on a different data sample. We didn't change the distribution of the sample.
What I mean is, let's say, on the coordinates, I
Mhm.
mean, first our x1 is like 2, and x2 is, for example, like 2. But since we double x1, it will become 4, and the x2 is still 2, so it will change the location of that data point, right?
Yeah, you change the, well, you please try to understand that way. You don't change the location of one data point. When you look at another location, you are looking at different data point.
Oh, I see.
So
Thank you,
each
sir.
point represents a different data. I think the great way to understand that, well, I will share after this lecture, this notebook. A great way to understand that is just to get your hands dirty and play with the examples here. Don't be afraid of changing things. You can see that I didn't use the existing demonstrations at all in this lecture. I just do everything from scratch. So I will encourage you to do the same. Just use the correct code for reference, but trying to build things by yourself. That will create a better understanding.
Oh, I see. One final question, sir. So we see there are carved lines, like in this demonstration illustration, there are like 3 carved lines, right? We have the pink one and the purple one. So if we didn't make it carve, it was still a line that is perpendicular to our W vector, right?
Let me think about that. It's not necessarily. It depends on the decision making part. If you are very naughty, I'm showing you. That could be the case, although nobody really use that. But if you really want, nobody can stop you. Like, if you do this, you will get a very funny result. And look, in this case, you don't have that single line to a single gradient to talk about, right?
Can I share my screen, sir? I think it will make my question more clear.
Okay, sure.
I think
I'm changing the first I stop share more, and then I need to change the share screen options. Okay, now you can.
Yep. Oh. Can you see my screen now? I will just use Paint.
Yes.
Yep. So when we learn perceptrons, we have vector X. Vector W, and we draw those lines. Sorry. My
It's okay.
drawing. These are perpendicular to our vector W. So from my understanding, by changing the value of x0, let's say we make it square, we change those straight lines. We change those straight lines into how can I say, curve one? Am I right?
It's
Is it a misunderstanding?
I won't understand that in this way. Although maybe this is right, but this understanding is really difficult to verify whether that is correct or incorrect. So
Oh.
my understanding would be like that. By doing this, I keep this without changing. I still keep this. What I was doing is now I'm now in a situation where this axis is x0 to the square. So previously, I have another space of x0 and x1. Then to change this space to this space, I can keep the x1, this point, to this point.
Yeah.
Sorry, this point, consider this point. This point, when I'm considering its coordinate in this direction, so
You can draw a new one.
this point,
Yeah.
the red point must be on the blue line here. And to consider this coordinate, we need to take a transform, such as maybe minus 0.15. Then I need to change that to maybe positive 2. So 2.25. Okay.
Yep.
And if I'm considering this point, maybe, so it will be on the same horizontal line.
Yep.
And consider maybe that is 0.8, then it will become 0.64 here. Okay.
Oh.
So this goes to here, this goes to here. And in such a way, if you do this same transformation on every single point in this space, you will change points in this space into this space in such a way of ramping that. And any geometric object, such as a straight line in the target space, when you considering all the points that will be mapped to this line will be some complex object, graphic object in the original space.
Oh.
In such a way.
I see. So if I play with the notebook, it will become more clear, I think.
Yeah. And you not necessarily need to understand the model in such a way. You can, you can go directly to mathematical analysis.
Oh, thank you so much, sir. I will stop sharing.
Hi, I have a question about assignment 3.
Yeah.
So in the assignment 3, say we should do more experiment and explain how we can improve our model, not just from our previous, not just presenting our previous assignment, right?
Do we have this? Or I don't think so. You. Oh, or I know what you mean. There is a point that is to ask you to discuss some issue in your previous implementation. That is very personal. It's about your effort of doing assignment 2. Of course, you didn't do assignment 2 in 5 minutes, right? You overcome some challenges. You debug something. You maybe find some hairy engineering stuff, like maybe your float number has issues, maybe your, I don't know what, but I'm very sure nobody just write that from the first line to the last line without any challenge. So it is to ask you to discuss a challenge that you have encountered. It's not let you to do new things. It's let you to discuss whatever you have encountered and you have overcome.
No, okay, okay. I have one more question. I came to the lecture a bit late, so do we have to present like record with our collab notebook, or should we?
It depends on you. You can record against a Colab notebook and you go through the notebook. That is okay. You can also compose some slides and talk against the slides. It is also okay. And you can choose to be present in front of the camera like what I'm doing now. And you can also choose to hide behind somewhere and just let your voice represent you.
Oh, okay, okay. Is there like a minimum amount of minutes? Because I'm doing perceptron and I feel yeah, may not take a lot of minutes for recording.
There is no minimum requirement of the time. There is a maximum requirement. You cannot exceed 5 minutes.
Okay, okay, okay. Thank you.
Okay. If that's it, thank you for everybody for coming. Yeah, thanks. See you next week. Bye. Okay.
Thank you, sir.
Yeah, talk to you later. Bye-bye.